Can you hear me now? Okay, sorry. Ah. I checked the sound before, and for some reason it was turned off. Okay, so just don't worry about the details. If you wish, there is a paper by Baker and Cousins. Okay, so this paper by Baker and Cousins tells you, gives you a prescription on how to use a minimum chi-square method for cases where the number of entries in the bins may be 0, 1, I mean, it could be also very low. So basically, use a chi-square if you have sufficiently large number of entries. If you have cases where you have low number of entries, don't worry, there is a prescription to do it. And if you didn't get all the details, just go through this paper and you can do it. Okay, last thing before we move to a different subject, how can we use a chi-square method to combine measurement, which is something I'm sure you are interested in. So if we have different measurements, yesterday we already saw that if you have a number of measurements of the same quantity, we can write a Gaussian likelihood. Imagine you have x1 plus or minus sigma and x2 plus or minus sigma. And yesterday we already saw that we can build a likelihood, which is the product of two Gaussians. If the two are measurements of the same quantity, these are distributed according to a Gaussian of x1 with parameters mu and sigma. And this also is distributed according to a Gaussian with the same mu and sigma. And we saw that the result, we can build the likelihood, which is the product of the two, and the maximum likelihood gives us just mu equal x1 plus x2 divided by 2, okay, which with an uncertainty of sigma. If we do the same with different uncertainties here, so imagine we have sigma 1 and this is sigma 2, the chi-square you have to minimize, basically minus 2 logarithm of the likelihood function is just the chi-square, which we can write as x1 minus mu divided by sigma 1 squared plus x2 minus mu divided by sigma 2 squared. Okay? We can then find the minimum of this chi-square just computing the derivative, and we end up with the minimum where we have that x is equal to, mu hat. The estimate for mu is equal, so better I also write mu hat here, is equal to the famous weighted average. So we can define a weight which is 1 over sigma 1 squared. Okay, and then I can write this in this way, so I can write W1 x1 plus W2 x2 divided by W1 plus W2. Okay, this is what we obtain, and the uncertainty that we get. So if you wish the variance of mu hat, so sigma square mu hat, is equal to the inverse of the sum of the variances. So if you prefer, you can write 1 over sigma square equal to 1 over sigma 1 squared plus 1 over sigma 2 squared. I don't know if you have done this, but the way to obtain this result is just to compute the derivative of this chi-square and set the derivative to be equal to 0. You solve the equation. Now, what happens if you know that there is correlation between the two quantities? So a way to extend the chi-square and take into account correlation is to write the chi-square in this way. So we write the chi-square as a vector times matrix product. So we have the two x1 and x2. We have mu, so we can write x1 minus mu, x2 minus mu, times the covariance matrix inverse. So this is sigma 1 squared, sigma 2 squared, and then there is the correlation term, rho sigma 1, sigma 2, 2 minus 1. And then we multiply by x1 minus mu, x2 minus mu. So if we have no correlation, this is just 1 over sigma 1 squared, 1 over sigma 2 squared, 0, 0, okay? And you get just the chi-square. So if this is not the case, this is the general way to write the chi-square. And we can minimize the chi-square in the same fashion. What you get here is just a matter of inverting the matrix and compute the derivative. I give you the result, which are interesting. And you get these. So you have mu hat is equal to something which is slightly different compared to what we encountered before, because we have x1, and instead of the weight, which is the inverse of sigma 2, we have this. We have sigma 2 squared minus, let me get the signs correctly, rho sigma 1, sigma 2, plus x2, then multiplies sigma 1 squared minus rho sigma 1, sigma 2. And at the denominator, you get this product, which is sigma 1 squared minus 2 rho sigma 1, sigma 2, right? Yes. Plus sigma 2 squared. So if you have rho equal to 0, so here are the terms which contain rho. So if you set rho equal to 0, this is exactly the weighted average you had before, because if rho is equal to 0, we end up with mu hat equal to x1 sigma 2 squared plus x2 sigma 1 squared divided by sigma 1 squared plus sigma 2 squared. This is exactly what I wrote before. So it's x1 1 over sigma 1 squared plus x2 1 over sigma 2 squared divided by the sum of the inverse squared uncertainties, okay? Now this is very interesting because this tells us that the weights may have some funny properties. One way to rewrite this, if we have the chance that the term rho sigma 1, sigma 2 is positive, this allows us to write this in a way which we can interpret. This would be easier with the slides because I'm just copying formulae. I'm not doing the math for it. But it is possible to demonstrate that if we define something like rho C equal to, rho C squared equal to rho sigma 1, sigma 2, and if we assume that this is greater than 0, which is not always the case. But in this case, we can write mu hat in a way which is very easy to understand. So this is x1 divided by, how is it? Sigma 1 square minus sigma c square plus x2 divided by sigma 2 square minus sigma c squared. And this is, and we get below 1 over sigma 1 squared minus sigma c squared plus 1 minus this thing. So basically what you do here, you take the uncertainty sigma 1 and sigma 2, you subtract in quadrature this that we can call common error. This is in some paper called this. And you basically have the weighted average. So this is just W1 x1 plus W2 x2 divided by W1 plus W2. And the uncertainty of mu hat squared is similar to what we considered before. So before I wrote, I actually deleted it. You remember the inverse of sigma mu squared is the sum of the inverses of the individual uncertainty. Here we get something more interesting because we get the sum of the inverses of the error subtracted the common error, sigma c square, okay, which is exactly what we had before, but in quadrature, we sum sub sigma c square. So basically, what is the prescription? We have some common error. We take this off. So it does not count on the combination, because just we weight taking into account the uncertainty where we subtract in quadrature the common error, and we just add in quadrature the common error to the measurement. So imagine we have some uncertainty because we measure some value of a cross section, okay? And you have an uncertainty which depends on specific measurement, and maybe we have an uncertainty which is due to the determination of the luminosity of the LHC. So if we measure two cross sections, both are affected at the same way by the luminosity uncertainty. So this is a common error. So basically what we can do, we can do the combination, subtracted this common error, the luminosity, and then we just add up this in quadrature at the end. Now, the real issue is that we may have cases where we have negative uncertainties, because if this product is negative, we may even end up having negative weights. So this formula still holds, but there are difficulties in the interpretation. So for those of you who are interested in the way that this can be interpreted, check a paper, where is it? Okay. This is an example where this method is applied. This is a combination of top quark mass by the LHC top working group. So this is a combination of top quark mass from different measurements in ATLAS and CMS. And here there are cases where there are negative weights. There's been a lot of discussion about how to interpret negative weights. These are not a pathology. This may happen. Just require a little bit of care in the interpretation, because when it's not obvious to interpret the common uncertainty like, I don't know, luminosity and so on, but there may be difficult entangled correlation between theory uncertainties, experimental uncertainties, and so on. This requires a little bit of care. And this approach is called BLUE, which stands for Best Linear Unbiased Estimator. Okay, so if you are interested, check the literature for this BLUE method, and you will find a lot of interesting results. More in general, if you do a combination of measurements which is based on this approach, you can, for instance, combine measurements where individual measurements are dependent on some more fundamental parameters. For instance, imagine you have a number of standard model measurements, and each one has some prediction which depends on the top mass, W mass, and so on. You may have a chi-square, which is a big matrix, which have, I don't know, measurement xi minus mu I, and this mu I may depend on top quark mass, W mass, Higgs boson mass, and so on. You have here the variance matrix inverted, the covariance matrix inverted, and here again you have this xj minus mu j, which depends on the same parameters. This may be a big chi-square with a big correlation matrix that takes an important effort to compute, but what you get at the end are very interesting results, because this is the way we use, if I can move forward and backward on this slide, to determine, for instance, standard model parameters. So this is a collection of measurements from experience of different sources like the experiment, Tevatron, and so on. And there are many measurements of cross-sections, asymmetries, and other observables that I don't have time to cover. But you end up basically with a big chi-square, which you minimize. And the minimization gets estimates of the physical parameters you want to know. The Higgs boson mass, the double mass, the top mass. And what you can do, you can exclude direct measurements of these quantities from experimental data, and you can compare the theory prediction with the direct measurements. Here you see, for instance, comparison of the fit without constraining the double and the top mass from experimental data and end up with this measurement, or you include some measurement and not the other ones. So you can do a lot of interesting cross-checks. Note here that this two-dimensional ellipse is marked at 68% and 95%, so you have to be careful that this, you see the width of these ellipses has been scaled from 1 sigma to 1.51 sigma. So you have to be careful about what I told you last time. So if it wrote 68% or delta chi-square equal 1, they make slightly different meaning. Okay, so I hope I gave you all the ingredients to appreciate this kind of things. And now I think we can stop here and move to the second big question that I presented you at the beginning of my lecture. So, so far we saw how to measure parameters from theory with fits of different kinds. Now we want to address the issue of a test hypothesis. Okay, so we can say, does the Higgs boson exist? Does supersymmetry exist? Does dark matter exist? According to the data I see. Okay, so do you have questions so far about this? Sure. This is, no, not necessarily. This is one source of uncertainty which you plug in. What is important is that it's a source of uncertainty which comes from the same kind of source for both, or for all the different measurements. So this could be a systematic uncertainty, could also be, well, usually, yes, usually if you have just statistical uncertainty, in most of the case, all the different measurements are taken from different data samples. If we have two measurements where you have overlap of the experimental sample, you may have also correlation due to the statistical uncertainty, because if you use the same data to do two measurements, the statistical uncertainty may have some common component. Okay. More questions before I move subject? Okay, so what we want to ask now to our data is the following. So we have data. Then we compare data to different hypotheses. Hypothesis 0 and hypothesis 1. And we want to say which is favored between these two hypotheses. So there is a sort of natural way to answer this in the Bayesian fashion, because I can give a probability to this hypothesis. So in the Bayesian approach, what I can write that the probability of an hypothesis H1 or H0 is the same given the data, is equal to the probability of having our data given the hypothesis times the prior probability of H1 divided by the probability of the evidence P of X. Okay? If we have two hypotheses, I can write the same for H0. And in the ratio of the two hypotheses, this denominator, which is the hard part to compute, you remember we have to decompose this and so on, in the ratio, the denominator cancels. So I can write that the probability of H1 divided probability of H0 is equal to the ratio of the likelihoods divided by the ratio of the priors. Or in other words, another way to say it, since the ratio of probability is called often odds, this is called odds of, let's say, 1 over 0, and this is equal to the likelihood ratio times the odds due to the prior PDF. So if this is capital O, okay, maybe I put, don't know, something like this. This is small o, I don't know, I put small o. So the posterior odds is equal to the prior odds times the likelihood ratio. And apart from some technicalities where we have to compute this likelihood ratio may be due also to some external parameters. So we have H1, H0 plus other parameters, and in those cases we have to do some integration, but I will not touch this. This factor is called the Bayes factor. And so we can say that we can transform the odds we have from the prior to the odd we have for the posterior, multiplying by this Bayes factor. And after that, we can say that if this factor is very, let's say, large, the hypothesis H1 is very favored compared to H0. So in this case, we can use the Bayes factor rather than the priors. So if you don't want to be sensitive on the prior, we just concentrate on Bayes factor. And if this ratio is smaller than 1, the hypothesis H0 is favored. So if we want to be, let's say, very certain about the fact that H1 is true, we can put a threshold here. I don't know. There have been thresholds which has been proposed, like, I don't know, if we have more than 150 roughly, we have a very strong evidence. If we have more than 20, we have a strong evidence. I mean, this degree of giving adjectives to this, to the value of this ratio are matter of convention, so I will not go any further. And basically, that's all we can do with Bayesian statistics. We don't need to do more. If you want to address the problem from the frequentist point of view, now the issue is a little bit more delicate. And I will formalize it a little bit here, because we have to do basically this trick and define more in general what is this p-value. So we slowly go to a general definition of this p-value that allows us to exclude one hypothesis, which is basically what we have done with the chi-square fit. Okay, so let's do let's give some basic definition. So a way to say whether one hypothesis is favored against another may be the following. So imagine we have some observable quantity, just one, but in general, at the end, we may have a very complex data set. So let's consider the simplest case where we have this value. And imagine that we have, for instance, you remember we already considered the case where we have these muons going through a detector and the pions. Okay, so if muons tend to cross a number of planes in a detector, say, and pions just stop earlier, we can put here, for instance, x could be the total path traversed by the particle within a detector before the particle stops. Okay, so pions will behave this way, and muons will behave this other way. Okay, so we can call this sigma, signal. Okay, in the plots I've done exactly the opposite, but maybe I can reverse. No, I don't have a plot here. So I supposed to draw it on the blackboard. So whatever we call signal background is, I will be consistent. So imagine that I have for instance, here this is called background, and this is called signal. How do I separate the two? So maybe I can put a cut here. Imagine I choose this by eye for the moment. So what I get is the following. If I say that my signal is what passes the cut, so it's above the cut, okay? So above the cut is signal-like. So this is my signal, okay? And a fraction of the signal is lost. So this is the area under this curve is what I called efficiency. Do you remember? And if I take instead the background is this one, and the area under this curve, I arch this in the opposite way, is the fraction of fakely identified pions, and this is what I call, do you remember, delta. Now there are some terminology which are slightly different in statistics. So in general, we don't talk about, in physics we usually talk about signal and background. Or maybe we can have the two different hypotheses. Imagine that we have a histogram where we have we want to reconstruct a mass peak, something like this, okay? And then we have some data. And here maybe I have a bit of excess, you see. Now, I can construct some observable, and we will discuss on how to do it. And the two hypotheses could be background only, or maybe background plus signal, okay? And this may be H0, and this may be H1. So in physics, we talk about signal and background. In statistics, mainly, statisticians prefer to talk about null hypothesis, H0. So we have the H0 is called null hypothesis. And H1 is called alternative hypothesis. A statistician prefer to call this delta, they call actually beta, and this is called, let me remind it, because I always forget, because this is not natural to physicists. So beta is called type 2 error, I think. Yeah, error of the second kind, and is basically the probability to reject H0 if H0 is true. We call it misidentification probability. So it's the probability of fake signal. Or if we, or fake positive, maybe. If we are using a language more close to medicine and biology, we can write fake positive. Imagine you are testing against COVID, this is the probability to have a fake positive test. And instead of epsilon, usually people prefer to use 1 minus alpha, where alpha is called fake negative rate, fake negative probability. And actually, alpha is this part here. Okay, so when you read statistical literature, you will encounter more this terminology. And in physics paper, we talk more about efficiencies and misidentification. Now, something interesting is how to determine where I have to put the cut. So if I change the cut, you see, if I move the cut on the left, I increase both epsilon and delta, or if you wish, alpha decreases and beta increases, and vice versa. So I can build another kind of plot, and I can here plot the efficiency, or if you prefer 1 minus alpha, and the misidentification, which is called beta, okay? So they go from 0 to 1, so they're bound to be within a rectangle. And what do I get with this cut? In the net cut, roughly, I'm accepting how much? 90% of the signal, so I'm here. And how much background I get? 5%, right? So I get something like this, right? So I'm more or less here, okay? Is it correct? Actually, usually one shows this the other way around. Most of the cases one have, I did this too quickly. In many cases, one has this efficiency here, which is 1 minus alpha, and the fake rate here. So let's draw this, sorry. This is the risk of when you use the blackboard instead of slides. Slides are always perfect. So I'm usually having high efficiency and low misidentification. So I'm more or less here, okay? what happens if I change the cuts? So if I move the cuts on the extreme left, I basically accept everything, so I am here. If I move to the extreme right, to infinity, I reject everything, and I'm here. And in the middle, you will have a curve that looks like this. Okay, so what happens if I have the two distributions that completely overlap? If the two completely overlap, I mean, or almost overlap, you have that efficiency and misidentification probability are identical, so I am basically on the diagonal. So the worst you can get is to be on the diagonal of this curve. A poor algorithm to separate the two looks like this, and the better algorithm moves to the corner. The ideal algorithm would be this one. For some reason, this curve is called, has a strange name, which I never understood why it's called this way. This is called ROC, and is, I think, receiver operator characteristic, something like that. I hope I remember the acronym correct. The fact that I'm being recorded makes me a little bit worried, but okay, you heard enough mistakes on my side, so it's okay. So basically, the issue that we have to face now is the following. If I have a single variable, there is not much to say to that. But if we have more than one variable, what is the correct approach that we have to take? So, for instance, selecting a signal which is the black dots from a background which is the red dots. I can do several things. Cut in two horizontal and vertical variables, and I have now to set two cuts, not just one. Or take a box or take an ellipsis. Which is the best way? Is there any preferred way to do this? So the question, maybe we can give it in 5 minutes if you would like to take a short break. Okay? And of course, we can, I can take questions in the meanwhile.
The red line there is the Q, is the case in which the Q distribution signal and background are completely separated.
Exactly. So if you have background here, then you have probability which goes to 0, and you have signal which is like this, so completely 0 here, and then this goes up. You can cut somewhere in between here and there. So here, if you cut, you are moving along one of these lines. If you're cutting here, you're moving along one of these lines. And in the middle, you have perfect efficiency and perfect misidentification. You are in this corner here. And this never happens in reality, unfortunately. Operating, operating characteristic, thank you. Thank you for Googling. Certo. Questo è il rapporto delle probabilità a priori che do H1 e H0.
Dipende da X?
Perché non dipende da X, vero?
Perché poi tutto viene a O.
1, 0, sì, una O, vabbè, se lo sono, O sta per odd, così come invece mettere pi avrei dovuto mettere Omicron, vabbè.
Ah, ok.
This just should have been a different letter compared to that one.
Però se io sono un complottista
Allora vince sempre.
questa diventa enorme.
E questa però è infinito, non c'è niente da fare. Il complottista non crede a niente.
Questa sarà gigantesca.
No, scusa, se sei...
La probabilità
Il complottista vince qua.
sono d'accordo nel
No, però...
mi abbiano fregato è uno.
No, allora, no, il complottista sta qua. il complottista c'ha la pari, non chiede niente, a una mette 0, quindi a questo punto questo è sempre o 0 infinito e vince sempre.
Non sono un complottista e voglio falsificare una cosa senza
Ok.
e rischio però di ottenere un grado
E
grande
devo andarmi a cercare.
un caso su 1 milione che succeda questa cosa
Ah.
senza che nessuno si sia messo d'accordo.
Ok.
Però sicuramente se tutti sono d'accordo nel fregarmi, mi fregano sicuramente.
Però qua devo andarmi a cercare l'osservabile che sbugiarda il complottista. Quindi se io sono bravo a trovare diciamo, la smoking gun, frego il complottista, però deve avere ovviamente un'evidenza molto forte.
Poi c'è il problema che
Com'era quella cosa di Carl Sagan? Com'era quella cosa, diciamo, incredible claims require incredible, no, except, com'era lì, mi ricordo, l'aggettivo non mi ricordo qual era. Extraordinary claim require extraordinary evidence. So, quindi qui diciamo,
questo è uno statement di
sì.
Perfetto, grazie.
All'inizio non abbiamo tirato fuori il Q4, perché il Q4 è la distribuzione che abbiamo nel minimo della likelihood.
Se,
Non ho capito bene
se la PDF è gaussiana, allora sì, se abbiamo una distribuzione gaussiana delle nostre osservabili, il chi quadro, che è costruito in questo modo qui, chi quadro è la somma con i che va da 1 a n di z con i al quadrato, ok? E si suppone che z con i segue una gaussiana che ha media 0 e varianza 1, ok? Quindi in questo caso io posso prevedere che questo qui segue un chi quadro con appunto una probabilità di chi quadro con n gradi di libertà, dove però questo n diciamo, diminuisce se io uso dei parametri per fare dei constraint. Cioè quando io scrivo, questo diciamo un po' velocemente, se io definisco x con i meno mu con i, che però dipende da alcuni parametri, ok? Se questo parametro dipende dal fit che ho fatto ai dati, questo in realtà diventa x con i meno mu con i, e dentro c'ho θ hat, ma θ hat a sua volta dipende da x1, x con n, perché il risultato è il fit. E quindi il fatto che questo qui in realtà dipende da mi toglie il numero di gradi di libertà pari al numero di parametri qui. Se ne fitto uno tolgo un grado di libertà, se ne tolgo n, diciamo, e questa cosa si può dimostrare che insomma continua a seguire un chi quadro, però devo toglierci i gradi di libertà.
c'è un'altra cosa che mi devo segnare. Quando abbiamo definito il p-value, abbiamo detto che la probabilità della bontà del sigma, perché, cioè, nel caso in cui il quadro sia perché allora io faccio un fit, trovo un certo quadro e vado a vedere, tipo questa è la mia distribuzione del quadro con una grado di libertà, vado a vedere dove sta quello sperimentale
Esattamente.
sulla mia distribuzione. Ma se sta prima, perché invece è meglio? Questo che mi sfugge.
Allora, se noi abbiamo un chi quadro che segue una certa distribuzione, ok?
E tipo quello sperimentale mettiamo da voi che
Insomma, questo dovrebbe essere distribuito più o meno, diciamo, secondo questa distribuzione. Quindi se io ne trovo uno qui o qui o qui, diciamo, sto abbastanza bene. Se sto in questa coda estrema, beh, posso dire la probabilità che un altro esperimento mi dia questo chi quadro o più è estremamente bassa. E quindi posso cominciare a dire, ragionando però in maniera bayesiana, è più probabile che sia sbagliato il modello. Però questo mi fa partire diciamo, il ragionamento bayesiano che come frequentista non dovrei fare.
Ma perché non lo faccio più simmetrico rispetto al massimo?
E perché i valori piccoli significano che i dati vanno molto bene rispetto al modello, anzi vanno talmente bene, questa differenza è praticamente zero. Però se sono praticamente zero, è probabile che quello che sta succedendo c'è una sottofluttuazione dei dati, oppure ho sovrastimato questi sigma. Cioè il modello descrive estremamente bene i dati, posso sospettare che la stima degli errori sia sbagliata. Però, siccome in genere questa è una campana che sale abbastanza presto, osservare il 5% qui, insomma, ci può stare. Ecco, se qui ho una coda che è 10 se quest'area è 10 a meno 4, 10 a meno 3, comincio a pensare che ho sottostimato i dati. Se ho 10 a meno, che so, appunto, 5% ci può stare, 1 su 20 capita. Okay, so I would like to thank two of you who spotted a couple of problems. So I also asked the director of who is making the final cut of this video that will be online. That first of all, by mistake I wrote that the ratio of the prior depends on x. So it was just a mistake on my side. So the prior, of course, do not depend on the data. When you define prior probability, you don't have any data available. So this is true. And then the name of this curve is receiver operating characteristic, and this has been Googled correctly, so sorry for writing this wrong. Okay, now imagine that we have a more complex data set, and we have 2 or even more variables. And in your case, I mean, when we are looking at experimental data, usually we may end up with a sizable amount of variables. I mean, we could have tens or hundreds of variables. So we have a theorem that can guide us, and we will take this as, let's say, as a benchmark, but in reality, it will be hard to compute this. And this is a theorem due to Neyman and Pearson, and we can build a quantity given our data set that is the likelihood ratio of the 2 hypotheses. So I write L of x given H1, L of x given H0, and this is called likelihood ratio, as it should. And you can decide that this is the variable you want to cut. So I say this must be greater than k. Greater because H1 is the hypothesis I want to prefer against H0. So I want to exclude H0. Now, what do I get? So I get the following. If this is lambda, in case H1 is true, I have large value of lambda. In case H0 is true, I expect something like this. And I have to put a cut here. So so this is H1 is true, and this is H0 is true. Now, imagine that I want to define which is the value of alpha. Alpha is 1 minus the efficiency, so it's this area here. If I want to set up a specific value of alpha, this means that on our ROC curve, I had 1 minus alpha beta, okay? So this has some curve like this. I want to set this value, okay? Then, which is the good property of this, which I called actually, let me introduce one terminology. This is called test statistic. And this means that you take your data sample, X could be something complex, could be H1, Hn, so there could be many variables, and you then extract from your data sample that can be complex a single value, lambda. Okay, so this is sort of summary of your data sample. It just returns you a single variable that is much more manageable. So if you decide which is your value of alpha, this k may depend on alpha. So let's put k sub alpha. And the nice thing about this likelihood ratio test statistic is that this has the lowest possible beta. So if I put this cut, I get the lowest possible beta. So better than this I cannot get. This means that this is the test statistics among all possible test statistics that gives you the best possible separation. So what else could I do? I don't know, maybe I could have done, here I have x and y, just ignore y, and I take x, okay? Or I, don't know, describe, for instance, here a sort of ellipsis around the central value, and maybe I use as value the radius of this k, okay? So if I use this approach or any other approach, I can do worse than this. So all other possible test statistics will go below this upper bound. Now, what is the real problem with this test statistic? That if you have many variables, you are not able to know exactly the likelihood function. So the likelihood function means that you, if you know the likelihood function, it means that you have in your multivariate space, you know exactly what is the probability distribution in more dimensions. So maybe these are contour lines that you have exactly under control. How do you exactly do this? In many cases, if you have a theory which predicts this, you can compute it. But in many cases, you just have experimental data, which are the effect of convolution between some theory prediction, experimental effects. You have uncertainty in the theory prediction, uncertainty on the estimate of experimental effects. So what you can do, you can put everything on the Monte Carlo, and you have a number of points, which may be more dense here and there. And from a finite number of points, it's not easy to determine the multidimensional probability. If you have a single variable, what you can do, you can just project all your simulation or control data on one dimension, and you have an histogram, okay? And this histogram approximates, within some uncertainty, your theory prediction. If you have two, what you need to do, you should define a number of beans which is much finer, and here you have n beans, here you have n squared, and clearly, if you have a higher dimension, you have n to the power of your dimensionality. So the problem of a large number of dimensions makes this very attractable, in particular for a very large number of variables. So how can one overcome this? There are different approaches, and we can consider a number of them. One is due to Fisher, and that's something very simple. This only works if the distribution are particularly simple. So something that is done here is that you take, imagine that you take this blue and this red sample, okay? What you can do, you can imagine to take a direction. I take this green direction, for instance, and I project the data on this direction, okay? So basically what I do, I take every point, I project this following the line which is perpendicular to the green direction. In this case, if the direction is this one, the projection gives you the blue, you see, and the red one. You see, the red one is more on the right and the blue is more on the left. If I take this direction instead, I have that the blue points are here and the green, the red are the other one. So maybe I did something wrong here. Because I don't see actually projecting on this. No, probably I've done the other way around. So if I project on this line, on the black line, okay. So I take this and I follow the projection along this direction. Okay, sorry, I project on this line. I obtain this. If I project along this line, you obtain this. So you may ask, which is the best projection? So you can take all possible direction, and there is a numerical procedure. Actually, there is an analytical solution to this problem, which allows you to find the best direction. And what you end up with is just an hyperplane, or a plane in 2 dimensions, but an hyperplane in more dimension, where you separate the two variables. And this gets a reasonable, let's say, separation, which is not necessarily this one. So you have another test statistics that behaves worse than this one. If the two distributions are simple and rather easy to separate, this may work. This, for instance, may not, this is called Fisher discriminant, is a Fisher linear discriminant because it's just, I mean, you project everything on a straight line with a linear transformation. And for instance, this is hard to imagine that could work here because here, if you put a plane, wherever you put the plane, for instance, this will keep you a lot of red components. So if you preserve most of the blue part, maybe you can put a plane here, okay, here. You can get rid of most of the background here, but you will keep all the background in this direction. So this, for instance, works better. And a way one may approximate this is to build a sort of what is called projective likelihood ratio. Let's try to define it. So instead of having a likelihood ratio, imagine that I have uncorrelated variable. So how could I write the likelihood ratio if the two, the n variables are uncorrelated? If those are not correlated, H1, H0. This would be equal to the product of the individual PDF. So I would have F1 of X1, F2 of X2, Fi of Xi, divided by the product of F, let's say this is F1, because there may be different probability distribution, Xi, H0, okay? Or if, maybe this is the redundant notation. Either I write this, or I write maybe like this. Okay? So basically, I have some probability density in each of the direction. And here in particular, this works perfectly because I have written the distribution and I've generated the data according to PDF which are factorized. This is the product of two Gaussians, and this red one is the product of two exponential terms. So in this case, this works perfectly. And if I manage to find the original PDFs, which are just a Gaussian and an exponential, in the likelihood ratio, they perfectly define which is the best test statistic. And in this case, I could write this analytic, and I don't do it for you, but the selection cut would be something very similar to this one, because here I have a lot of event with a high density of the Gaussian terms, and around I have a lot of event with only background. Now, you are not always lucky in this way, because you may end up with other distributions, and let me see if I have quickly, no. Maybe you end up with something like this, you see? Or something like, I'm spoiling, something like that, okay? Here, it would be very hard to define the likelihood in projective way. Let me not spoil too much what I'm going to do. And many algorithms that are used in energy physics, but not only in energy physics, rely on machine learning. And here you see an example of machine learning. So what do we want to do? We want to write a test statistic X is a vector of data, so is and this may depend on many parameters, W. So we would like to get this as close as possible to the Neyman-Pearson limit and approach a performance when we do a selection which is as close as possible to an optimal solution. The method which are applied are often sort of opaque to the user. This is an example of how the. So we will give you a short introduction to some machine learning concept, seen from a statistical point of view. I will not go deep into the description of the machine learning algorithms because this would take much more time. But for instance, how is this a model built? So you have a number of variables, okay? You built up a model where you basically, for every node, you take a number of inputs. Maybe the first node you see get as input consider this node here. This gets as input x1, x3, x, I call p, I am calling n actually here. So imagine I have x1 here, x2, and xp or xn if you prefer. And the way I get the output is twofold. So first of all, I assign weights to each of these inputs. So this is 1, 2, 3. So I do sum of wi xi. And maybe I can add also a term called bias, okay? So a weight that is multiplied by 1, not just by one of the variables. So this is just a linear transformation. And the issue here is that you want to have as output of this classification something which discriminates between two different cases. So I would like to have that lambda is close to, let's say, 0 for the hypothesis H0, and is close to something like 1, for instance, for the hypothesis H1. Okay, this is what I would like to get. And then there is some overlap in between, I cut and I get my discrimination. So this is something which should be between 0 and 1. And the linear combination does not fit it. So usually, if this is the output of the linear combination, I take some function that, given y, transforms this y into an output that is between 0 and 1. So something which was very popular in the past decades was a sigmoid function, so something like this. Okay, so for instance, would be something like 1 divided by, so we build phi of y, where phi is equal to 1 over 1 plus e to minus lambda y, okay? Is this correct? Because for lambda equals 0, you have 1, so this is 1/2, okay? And then this has an asymptotic, if this is goes to infinite, this goes to 0, and then this tends to 1. For negative value, I have the limit is 0. In more recent time, computing has evolved in such a way that there are better algorithms compared to this one, which have some numerical difficulties. So you will find in literature also something which is much more simple than that. For instance, you have nowadays something called the rectifier linear unit, something like that. Okay, and the reason is that in this case you can compute the derivative much easier. This is just a piecewise straight line. And here the derivative you can compute, but it's lower and also has some other difficulties that I will not encounter. So how are these weights determined? So what I get is the following. So each node has these weights. Then you have a number of different nodes. And then you do the trick once again. So you take the output of each node, which is something between 0 and 1, and you pass it to the next node in the layer. You may have a number of hidden layers up to the final layers when you have, in this case, just one output. And the output is something between 0 and 1, and you take this as discriminator. What's the advantage of this, of some technology like this? There is a theorem that says that given a neural network with just a single layer, if you take a number of nodes which is sufficiently large, so you take your input x1, x2, xn, okay? These are the inputs. And then you have a number of nodes which is sufficiently large, and so on. You do this. you can basically approximate any possible function if the number of nodes is sufficiently large. So if you optimize the weights, and the way the weights are optimized is not very different from the way a best fit is done. How do you do a best fit? How do you minimize a chi-square? So you take a chi-square, you take an initial value of the parameter, you see? What can you do? If the derivative of the chi-square is negative, you have to do a step back. If the derivative is positive. If the derivative is negative, you have to make a step forward. So basically, you have to follow minus the derivative, or if you are in more dimension, you have to follow minus the gradient of the chi-square as a function of the parameters, okay? And how big must be the steps? Usually, if the step is proportional to the gradient, you get a reasonable convergence, because as long as you move close to the minimum, your gradient gets closer and closer to zero, and here you want to make smaller and smaller step, because otherwise you overshoot the minimum. So this algorithm in general is called gradient descent. And it's suitable to solve this kind of problems with a lot of complications and a lot of let's say numerical issues. But what's more important, it turns out that even if in theory this model can approximate any function, so it can approximate also our likelihood ratio in a way which is satisfactory up to the level of precision that we want, in practice, this method becomes harder and harder to train, may require a huge number of nodes. So nowadays, we prefer, for complex problem, solution where we have a larger number of intermediate layers, and this makes our network deep, and this is makes the computer algorithm a little bit of a nightmare to be trained. So you will find a lot of literature, which I won't enter here in the details, but that's why you now find more and more tendencies to use these deep learning strategies. So how can we see this from the point of view of, let me see if I'm, okay, from the point of view of statistics. So let's take back instead of going through the details of the algorithms, let's see how we can consider machine learning from the point of view of statistics. So this is a very simple machine learning problem. So instead of trying to have a function which tries to guess between 0 and 1, I have another function which addresses a different problem. So this problem is called classification. So you have two classes, 0 and 1, and you have to assign some value of your data to one of the two classes, okay? In this case, I want to do another problem which is, again, can be addressed with machine learning, even with neural networks, and it's called regression. And the regression is just a fit. So you take an input, x, and you want to determine an output. And how can you do that? So here are some data, the red spot, which are extracted from a theoretical model. The theoretical model is this function. I don't tell you which is this function, okay? And I try to fit this function with a polynomial. Now, how complex can I grow the model? The model here is let's say, the structure of the network. My model is, the complexity of the model is given by the degree of a polynomial fit, which I want to apply here. Here I apply a polynomial of degree 3. And, is it satisfactory to you? Do you think that this works in a reasonable way? Well, not too bad, but actually you see by eye some discrepancy compared to the original model. And here is what I do if I try to change p to different degrees. So this is a straight line, horizontal line, okay? This is a line with a possible slope. This is a parabola. Third degree, the one which I showed you before, fourth degree, fifth degree, and so on. And now you see that there are nice features here that we can spot, and that tells us a lot of how machine learning works. You see that initially you have a model which is not enough complex. Imagine here you have very few nodes, okay? And this model is not sufficiently complex to describe our underlying true function, okay? Then I add complexity. And at some point, I see that the complexity allows me to model and get closer and closer to the function. But then if I make the model too complex, what I get is that the polynomial starts to follow the data very closely. You see here, it's starting to follow the fluctuation of the data and gets so close to the data that it starts to depart from the original blue function that it is what I originally want to model, okay? So this is called underfitting, and this is called overfitting. Or if you prefer, this is undertraining, and this is called overtraining. Okay. Eventually, if I add a sufficiently large number of parameters, I may have a polynomial that passes by all the possible points. So I have basically a spline. Okay. And now there is an interesting way to understand how this effect works and what is the how can we quantify this in some way. So I can take as a quantity that I want to minimize what is called mean squared error. So it's the expected square error in our notation. And this is the expected value of what? Of 1 over n. And we sum from I equal to 1 from I equal to n. And we have the value y sub I star are the vertical position of the point, minus the function that you fit from your points, okay? So if you wish, this is the function fitted at the point xy, x sub I. If I consider just one of these points, okay, I can call it, for instance, I can call theta hat the fit value at a given point. Okay, I drop the subscript I for simplicity, and then I call theta star the value that I measure. There is an interesting and very simple to demonstrate theorem that tells me that the variance of theta hat, right? The expected value of the uncertainty square, so is epsilon squared is the distance only for a single point, okay? So this is the epsilon total, okay, if you wish. Can be decomposed in this way. We can take the variance of theta hat plus the bias squared of theta hat plus the variance of theta star. So what are these terms? The variance of theta star is just the error. So this is sigma y, okay, and squared. And we cannot do any better than this. So points have their intrinsic fluctuations, and we cannot improve this. But the variance and the bias of the estimator, this depend on the model. So depend on the fit that we are performing. So let's look at two things. First of all, we have two kinds of estimates of this epsilon square, okay? If I take the test sample, which is this one, okay, I measure the difference between the points and the fit, which I do with the same points. So I'm measuring the distance between the red points and the orange curve. And this gets better and better, because as the more complexity I add in the model, the more the fit follows the data. So if I look at the trend of this epsilon square on the same model which I'm using for fitting, this gets better and better. So this goes down, you see? And at some point, this may even reach 0. Because if I have a number of parameters which is equal to the number of points, this completely constrains my parameter. But what happens if I take another sample which is extracted from the same function? So imagine I extracted a second red sample randomly around this blue curve. If I take an independent sample, I start to get, on average, the difference between the fit curve and something which is extracted according to the blue line. So in that case, I'm not getting better because the orange curve follows this very specific random extraction. But if I generate another one independently, this gets, at some point, even worse. So if I add complexity, the fit describes better the data up to the point where it starts to overfit, and then another independent set is somewhat worse than this one. So this is not really too much worse, but there are cases where this may even grow worse. How does this happen? So this is an example. I take p equal to 4. The blue line is let's say the truth model, the true model, and these are many, I think 50 randomly extracted sample and 50 randomly extracted fit. So you see that there are two things. One is how at a given x the different fit fluctuate, and this is the variance. Okay, and you see that this is not identical along the different points. So here, for instance, the variance is somewhat higher, here is somewhat lower, and so on. Okay, and this is the bias. The bias is how, on average, the gray curves depart from the blue curves. So here, for instance, this is a good point. The bias is low, and this is where we are. If I'm here, the bias is very high. And see that this is not constant, and depends point by point. So I can add the bias in quadrature and the variance, and obtain a sort of combined bias variance estimate. And I can see that actually the total uncertainty, the red one, is the sum, you see, of the variance plus the bias squared. And the two contribution is something that you can see here. So the bias goes down up to a certain point, and the variance goes up. Okay? So this tells you that there is a trade-off between bias and variance, and it's something that you should take into account when you do machine learning. And you cannot grow the complexity of the model arbitrarily, basically because otherwise you start to overtrain. Okay? Now, overtraining in more dimension can also be seen in this way. So this was a simple example. When you train a machine learning algorithm, you start to have a separation of signal and background according to your discriminator, which is not the ideal Neyman-Pearson test statistic, but is the one which is dictated by your machine learning algorithm. This is a reasonable separation where you still have imperfect separation unavoidably because you have some red points which are selected as signal and some blue points which are signal which are rejected, and this is life. And then you can optimize this by setting a different curve and so on. But then you can also run into this problem. So you start to follow the details of the individual point, and you start here to really overtrain because you are following the fluctuation of your sample. And if you have another independent sample, you may end up with a performance which is completely different from this one. So that's why when you test, when you test the performance of a machine learning algorithm, you want to have two independent samples. One to train your algorithm, so to find the parameters of the network which optimize by gradient descent the response, and then another to test how actually the performance are on an independent sample. Okay. Now there are other algorithms that we can find and you can find in literature and in your experiment. For instance, one is based on the so-called decision trees. So decision trees are a very simple way to take a multi-parametric space and split it into different regions, and you can start to subdivide again and again. So maybe let's take two variables, x and y. Okay, maybe let's start from the first variable, or do you want to take this This is an example from a paper which originally introduced this in physics. Number of photomultiplier hits, energy, radius of some quantity. So these are just observable quantities, okay? So let's call it X, Y, and Z. So maybe, first of all, I take X. So let's take some points which I call signal, okay? Like this. And some points which I call background. Maybe we have some overlap here, okay? So first of all, let's put as first selection variable X. So I have to put some cut to separate signal and background. Maybe I put it here, okay? So this is X cut, number 1. So here I separated background on the left and signal on the right, not perfectly. So maybe I start to get the second variable. I can take, for instance, a cut here, okay, in this region. And maybe I can put another cut here. I don't know where to cut. Maybe put here another cut. So I have two regions. One where I take background, well, two where I take background, and two where I take signal. And then I can start to split again. Here I'm happy because here basically I have only signal. Here I could also be happy there is just one signal overlapping with background, so it's a pure sample. So this is almost okay. This is okay. And here maybe I can split again. So I can put another cut here. I can say that this is signal and so on, and here I do again. At some point I stop, okay? And imagine you can do this on many different variables. So if you add a large number of branching, you end up doing overtraining. So we have to stop at some point the model and simplify the output. Does this model work? Not very well. This is called decision tree, and a single decision tree does not really work well in classification, but it is a model which tends to have a large variance, but a small bias, okay? So what you can do, you can combine different trees, which need to have some randomic, I mean, if they are all identical, you don't gain anything. If you add some randomness, for instance, you determine a tree from a subsample of the data and another tree from another subsample, or if you use different subset of the variables, or if you iteratively maybe reweight events in such a way that the next tree is updated with respect to the previous one, you may get better and better performance when you combine the result of all the trees and you average them with some algorithms. Okay, I don't go into the details, but you may find algorithms that are called random forest, where you basically choose many different random trees, or you have the boosted decision tree, where you start from a tree, then you apply weights which enhance the region where you have poor classification in such a way that the next tree is better at classifying the region which have poor classification in the first one, and so on. These are called boosted decision tree. And now there are also more recent technologies where instead of giving just an answer 0, 1, they return some parameters, some weights, which can be optimized with some sort of gradient descent. So you have this algorithm called extreme gradient boost. There is no time to go into detail, but you will find many literature. And now I can try to show you how some of these work in practice. This is, for instance, a case where we have some strongly linear, strongly nonlinear distributions. You see, you cannot really factorize the PDF into dimension. If you project on this on the horizontal axis, you have sort of a bump here, and on the vertical axis you have a bump there. But if you, if you have independent variable, you would expect a blob here. So this is how a linear classifier works. It's basically, this is not exactly Fisher linear classification. This is called support vector machine, but that's something very similar. So find basically a line oriented in an optimized way in order to separate the two distributions. And you see that if you take a diagonal line in this way, you may actually separate the two. So if you project on the direction which is perpendicular to this line, you end up with some output which is more or less like this. And you have, decent separation, not perfect. Note the way it is presented. So here you have some data which have been used for training, but here you compare the output you got from the train sample, so it's the histogram, is the blue histogram, to the output you get from a completely independent sample. So you generate a sample, you split in two, one you use to train the network, and another train the network in this way, just to define the optimal direction in which to cut. And the other you use for let's say, testing of the performances. So you see that the two have reasonable agreement, so this means that there is not very big overtraining. This level of discrepancy here indicate the level of overtraining that you get. This is instead a neural network with a shallow configuration that I think I wrote at some point which were the parameters. I think there were, I forgot the number of parameters, but if you are curious, I will dig into my code and will show you. So basically, this is a single hidden layer with, I think, is something of the order of 20 nodes in a single layer. And here, the selection you get is something which is strongly nonlinear. You see, the network is able to disentangle the two distribution, and the selection you get is along this way. So the blue one are the more extreme value of the network, and are the one close to 1, and the red one are the one close to 0. Okay, and you see that there is some overlap. This is much, much better than before. So here you have a substantial overlap. Here the overlap is very, very small. If you do something more, so I add a second layer, you see that compared to the first one, you increase a little bit the separation, increase a little bit the separation. And if you have more or less the same performance, and if you increase even more using a deeper structure, I think it had 3 or 4 layers with a substantial number of nodes, you have really an output which follows closely the distribution and have this kind of separation. How does the output look like if you have this random forest algorithm? So you mix randomly a number of decision trees. You see that the decision tree tries to cut the space into rectangular areas, and you combine many of them. So you end up with this final structure where you clearly see the discreteness in the number of trees which have been generated. You see? And here is what you get. So it does a very good job. We can compare this with the extreme gradient boost that more or less is similar. Usually this second one has slightly better performances because there is a better optimization of the parameters. And here is the ROC curve. So you basically have the linear classifier is pretty, weaker than the other ones. The shallow neural network is the worst one, but then all the other more or less perform the same. You cannot really distinguish different curves. Let's take another example. And this is this chess-like shape. So I did not exactly randomly extract the data on a chessboard, but there is a bit of overlap here. You see, they are not exactly distinguishable. So if you had the real chessboard, you can just put some cuts, and that's what the best you can do. And then let's see how the different algorithm works. So the linear classifier fails miserably. Basically, the distribution for the red and the blue largely overlap because there is no way to cut with a straight line these the two distributions. Okay. If you take the shallow neural network, a single node is not very good at doing discrimination. Basically, see there is a important overlap. Just the edges have been recognized. You see this corner here, this here, this here, this here are classified correctly, and this fall up in the extreme part, but the inner part is not very good. But if we increase the number of nodes, here it tends to follow some diagonal shapes, you see, and the overlap decreases. If you take a deeper network, you really mimic very well the structure. But clearly the decision trees where you can just cut in straight rectangular interval the space it gives also a very good separation. In particular, the XGBoost works rather well. And let's look at the ROC curve. The base is actually the deep neural network, but it's very close to the to the extreme boost, the green one, you see there is small separation, and then the other follow, but the linear classifier and the shallow neural network really don't do a great job at all. Other test which I tried is these intertwined spirals. So these are spirals which are really mix the data, but you can still recognize them. So let's see how this works. And we have a linear classifier which fails miserably, shallow neural network that does the job up to a certain point. Let's say the middle depth neural network does something better, and the deep neural network is even better and is able to classify pretty well the shapes. Let's look at the random forest. Good job again. And the extreme boost is even better. So the score is the following one. The best one here in this case is the boosted decision tree. Then we have the neural network with deep structure, and then the other follow. There is actually a theorem that says, it's called the no free lunch theorem, that says basically there is no first principle choice between the different one model or another. You have to try different possible models because according to the structure of the data, some algorithm may perform better than the other. So the reason why in high energy physics, in particle physics, we had in the, let's say, 90s, 2000, there was an improvement, a preference of algorithms based on boosted decision tree was because the development of deep neural network was not sufficiently advanced to have comparable performance. Now, many algorithms prefer deep neural network, and you see there's a lot of trends there, in particular because there are also other possibilities to build up more complex algorithms. I didn't enter into the details here because the field is really too vast. But there are possibilities to exploit very complex data structures. For instance, imagine that you want to, for instance, analyze an image. An image is made of pixels, which are maybe really many. So you can have a bitmap image, which is, I don't know, could have tens of millions of pixels. So each pixel has a red, green, and blue components, so even times 3. And why maybe we interested in physics to study this kind of problems? Because if you have calorimeters usually are divided into cells. Each cell gives us some energy, which can be higher or lower than the neighbors, and the pattern like this may be similar to an image. Or there are also neutrino experiments which are modular. So there are some experiments which are just based on internal structure made of detector which are brick-shaped. So you really have the same module again and again, which repeats over a large area. And wherever you get a neutrino, you may have a signal which may be identical if displaced in any other position, which depends on where the neutrino interacts with this detector. And how do you handle such a such a large amount of data? In this case, there are algorithms which take just a subset of the pixels. Imagine you take, I don't know, 5 by 5 pixels. Here we have 25 nodes, basically. And imagine you train a small, this is called filter. In order to spot a particular feature here, maybe you train this to get a pattern which is, I don't know, something which is like this, okay, or like another shape. And you can move this 5 by 5 kernel or filter in all different places in this image. So you move down from a number of parameters which is very hard to manage to a reasonable number of parameters. Now imagine that you spotted this. At some point in this image, you have a number of patterns like this. Then you end up in the response of this filter that pixel by pixel, when you displace this node, may highlight this feature or not. So you end up that you basically have 0 response, and then in this area you may get some highlight that you spotted this feature. Imagine that you have another filter which spots inside a pattern like this. You may end up with a different response where you can find positive answer only in the places inside the image where there is this kind of feature. And then imagine that there are subsequent layers which take as input the different features, and then maybe if you train a network to spot, I don't know, an eye which is, I don't know, a concentration of pixel here, another eye here, and maybe a pattern like this, you may train the network to spot a phase or something like this. And these are so-called convolutional neural networks, which is just one of the examples of very complex architecture that these neural networks can take, and that start to be actually are exploited nowadays also in particle physics for special structure of the data. You may have data structures in form of trees or graphs, and there are networks that map the structure of the data. So this is really getting a complex field, and you have recently a variety of tools which is growing in complexity, and most of all as a community of developers which is also broadly distributed outside the energy physics. This is clearly, you know, it's used for image recognition, for social network, and so on. So I will stop here about this sort of overview of machine learning, and then tomorrow we move to the last subject, is how to claim a discovery. So we saw today how to use this technology of hypothesis testing to test one hypothesis against the other, and tomorrow we'll concentrate on how to test the hypothesis that a new signal is present in data, and compare this with the hypothesis that there is no signal in data. So we will see how to claim a discovery. Questions?